All right, so I am not going to read through the whole question, so I kind of expect you to have this open as I go through these so that you know what the questions are asking. And I'm just going to go through the solutions for the FRQs. So here for the first one, it's asking in which trial does the disk have a greater speed at 0.5 seconds? So remember, the area underneath these graphs will give us the the impulse, right? So if I get the area here and I compare it to the area here, that will give me the impulse on both of those. So right, for both of these, we're finding delta P by looking at area. And in both cases, the disk's mass is the same. And also in both cases, the initial velocity is 0 and the initial momentum is 0. So if the impulse is the same, that means that they will have the same velocity, for example. And it turns out that's just what happens, right? So if we look here, this one is a rectangle, and the area of that rectangle is just base times height, which is 4.5 times 1 units of Newton meter. So this is 4.5 Newton meters, or wait, no, not Newtons per meter. Newtons times meters. My bad. So that's this one. This one is a triangle, right? And if we look at that triangle and we do 1/2 base times height, the base is 0.3 and the height is 3, right? And if we do this, we also get 4.5 newtons times meters. So the impulse here is actually, it's actually the same. Okay, students found that in trial 1, the disk took time delta t to slow down. All right, so this one is trial 1. And now they're asking, well, if the students repeat this, but with the disk made of the same material but twice the mass, and the force applied looks the same, right? So the graph is the same. How much time will the new heavier disk need to slow to a stop on the rough section, right? So remember, there's these two sections. So they're saying that we're going to double the mass of the disk, right? So we're going to make this disk twice as big, and we're going to apply that same initial force, and as far as it takes to come to a stop, but we don't care how far, we care how long it takes to come to a stop if we double the mass of that disk. So if the force time graph looks exactly the same, what that means is the delta P is going to be the same. It's not going to change if we make the disk heavier. All right, so delta P is the same. And in order to come to a stop, remember that the force that's exerting impulse to stop it, right, as it's stopping, the free body diagram looks something like this. There's friction, normal, and mg. So the force that exerts impulse to make it stop is friction. And we know that the magnitude of the impulse applied by friction, it has to be equal to delta P, right? Because if it's stopping, there needs to be the same amount of impulse applied to the left on this as there was originally to the right. Right? Or if we could just write it out, right? So as it's coming to a stop, we know that delta P is equal to F delta T, and this is P final minus P initial, which is M VF minus M VI, and this is equal to F delta T, and in this case, as it's coming to a stop, it's friction force, so I'll just write curly F to indicate that that's friction force, and VF is 0, so we've just got negative MVI is, or maybe rather than that, I'll just write P, just PI. I don't know why I need to write that. Negative PI is equal to F delta T. And this PI is the same. No matter, it doesn't matter that the disk is twice as heavy, because if the force versus time graph looks the same, that means the same amount of impulse is applied to the disk. It doesn't have the same velocity if it's doubled, but it will have the same momentum when it reaches the rough patch, right? Because the same amount of impulse was applied to it. So it will have the same momentum when it enters the rough patch. So now we know that the amount of impulse applied needs to be equal to this. So what that means is, in this new scenario, if we take f delta t and kind of fill in some of the variables, right? And I'm just going to look at the magnitudes of these. So the magnitude of f delta t will be mu times normal force, which is mg, times delta t. Now, like I said before, this is the same in both scenarios, or I guess both trials, or no, both times, right? Because we're just looking at trial 1, but we're doing it with one that's twice as heavy. That's the same. The mass is doubled, right? They're telling us the mass of the disk doubles. So that delta t is actually going to go down by a half. So the answer is that we could say something like delta t new is equal to 1/2 the original delta t. It'll take less time, right? And this is essentially because if the disk's mass is doubled, well, it enters here with the same momentum as it did before, but there's twice as much friction force because it's twice as heavy. Therefore, it takes half as much time to come to a stop. All right, I hope this was helpful.